Welcome to all of you. Now we discuss about 2020 paper CC-5 real analysis mathematics honors multiple choice question. The question paper 2020 paper CC-5 mathematics honors. Question 1a, limit x tends to 0 1 by 1 plus e to the power 1 by x equal to, correct option is 4, does not exist. Here fx equal to 1 by 1 plus e to the power 1 by x and x not equal to 0, as x tends to 0 plus 1 by x tends to plus infinity, so 0 plus, so this 1 by x tends to plus infinity, so e to the power 1 by x tends to plus infinity, e to the power 1 by x tends to infinity, so e to the power infinity, that tends to infinity, this tends to infinity. So limit x tends to 0 plus 1 by 1 plus e to the power 1 by x equal to 1 by infinity, this equal to 0. This is the 0 plus right hand limit. So this is equal to f0 plus 0. Again, as x tends to 0 minus 1 by x tends to minus infinity. This is the minus infinity tends to minus infinity 1 by x. So e to the power minus infinity tends to 0. This e to the power minus infinity tends to 0. So limit x tends to 0 minus 1 by 1 plus e to the power 1 by x equal to 1 by 1 plus 0. This is equal to 1. This is the left hand limit f0 minus 0. So right hand limit not equal to left hand limit, hence the limit x tends to 0 1 by 1 plus e to the power 1 by x does not exist. Actually, the graph of e to the power 1 by 1 plus e to the power 1 by x is this. This is the straight line. This y equal to half, and this is the 1. So this is the graph of this. 0 plus this tends to 0, so this is equal to 0, right hand limit, and this is the 1, so left hand limit is 1. Next question. Question 1b, if limit x tends to a mod of fx equal to mod of L, then limit fx x tends to a equal to, nothing can be said. Now we have a theorem. If limit x tends to a fx equal to L, then limit x tends to a mod of fx equal to mod L. But the converse is not true. And this limit x tends to fx x tends to equal to L, then for any pre-assigned positive epsilon, there exists a positive delta depending on epsilon such that mod of fx minus L is less than epsilon for all x belongs to the dilated delta neighborhood of C in dash delta C. Now mod fx minus mod L, this less than equal to mod of fx minus L, this less than epsilon. And because we know from triangle inequality mod of x plus y equal less than equal to mod x plus mod y, and from this inequality we can easily deduce this mod of mod x minus mod y, this less than equal to mod of x minus y for all x belongs to the deleted delta neighborhood of C. So obviously limit x tends to a mod of fx equal to mod L. So if limit fx equal to L x tends to a, then we get limit mod of fx equal to mod L x tends to a. But converse may not be true. For an example, consider this example, fx equal to 1 when x is rational numbers and fx equal to minus 1 when x is irrational numbers. And let a be limit point of the domain of the definition of the function f. Let us choose here a is domain, these are real number, two set of real numbers. Let us choose epsilon equal to half. and we take 2 points, arbitrary 2 points x1, x2 in dash delta a, delta neighborhood of a. We choose any 2 points x1 and x2 real numbers such that x1 is rational and x2 is irrational. So if x1 equal to 1 and if x2 equal to minus 1 according to a choice. So mod of if x1 minus mod of minus if x2 is equal to 1 minus minus 1 is equal to 2, not less than equal to half. Now Cauchy's principle gives D is subset of R and A maps from D to R. We have finite, we have function. Let A belongs to D dash is the limit points of D. A necessary and sufficient condition for the existence of limit extends to fx is that for a preassigned positive epsilon, there exists a positive delta depending on epsilon such that mod of fx1 minus fx2 is less than epsilon for every pair of points x1, x2 in dash delta A intersection D. Hence, limit extends to fx does not exist. But mod of fx equal to 1 for all x belongs to R, and we can easily get limit extends to a mod of fx equal to 1. So, nothing can be said from this definition. Next question 1c. If fx is continuous on the closed interval 3, 4, then in 3, 4, correct option is 1, mod of fx is less than or equal to m for all x belongs to the closed interval 3, 4, where m is a positive number, m is a positive number. We can find a positive number m. M is not a supremum. Maybe supremum also. Let I equal to the closed interval AB be closed and bounded interval, and the function A maps I to R be continuous on I, then A is bounded on I. Then infimum fx, x belongs to the interval I, less than or equal to fx, less than or equal to supremum of fx, x belongs to I, for all x belongs to I. If I is the closed and bounded interval, then f function, and if be a continuous function on I, then this theorem says that it is bounded on I. So there exists a positive real number m such that mod of fx is less than m for all x belongs to I. And this is the function, this x-axis is the y-axis. Suppose this point a 3 and 4, this function is this. So mod of fx from this part, and this from 3 to this point, this mod of fx is this part. So this function, this is the graph of mod of fx between the interval ab or 3, 4. So this function mod of fx is less than m. This m may be a supremum or not, any positive real number. Question 1d. Fx equal to 1 minus x when x greater than 0, fx equal to 2 plus x when x less than 0, fx equal to 1 when x equal to 0. Correct option is 4. Limit fx extends to 0 does not exist. So we draw this graph. Fx equal to 1 minus x, x is positive, so this is this, x is greater than 0, not equal to, and fx equal to 2 plus x when x less than 0, so this 2 plus x, and fx equal to 1, this point is 1, x when x equal to 0. First we find the right hand limit of fx, so right hand limit from this one 0 plus, so we get 1 minus x is equal to 1, and left hand limit 0 is equal to 2 plus x equal to 2, and f of 1 equal to 1. It is given that f of 1, f of fx equal to 1 when x equal to 0. So left hand limit and right hand limit not equal, and hence limit extends to fx does not exist. Question E. If maps from set of real numbers to set of real numbers defined by fx equal to mod of sine 1 by x not equal to 0, and 0 when x equal to 0, then the oscillation of f at x equal to 0 is option 3, 1. Fx sine 1 by x, mod of sine 1 by x, the graph is this, and is so limit supremum of this 0 plus f0 plus limit supremum limit infimum f0 plus f0 minus limit supremum f0 minus, so supremum is 1 and this 0, f0 minus is 1 and f0 minus 0, infimum is 0, so maximum is 1 and small mf is 0. So f is the discontinuous at x equal to 0 point of oscillatory discontinuity, and the saltus is the oscillation at 0, mf capital mf minus small mf is equal to 1. You can draw this graph. Fine. This is the graph. This point is 1. Mod of sine 1 by x. This is the mode of sine. This is 0. This is x-axis. This is y-axis. If we enlarge this graph, this is the point 1. This is 0. So limit sub is 1 and limit imp is 0. Limit infimum 0. Limit supremum is 1. 1 and 0. Either left hand side or right hand side to 0. Next question. If let fx equal to minimum x comma x square, x belongs to R, then identify the correct statement. Correct option is 3. F is not differentiable at two values of x. Here the graph y equal to x square and this is the graph y equal to x. So minimum x comma x square. So when negative x, for negative x, minimum is this branch y equal to x, and from 0 to 1, when x equal to 0 to 1, minimum is for this y equal to x square, and when x is greater than 1, and we get x equal to y equal to x is the minimum range. So f is not differentiable at the point x equal to 0 and x equal to 1. This is the fx equal to x when minus infinity less than x less than 0 and 1 less than x less than infinity, and x square if 0 less than equal to x less than equal to 1, and limit extends to 0 plus fx equal to 0. Limit f extends to 0 from right hand limit of this function, this is equal to 0, and left hand limit also 0, and functional value at the point 0 is 0 also. So our function is continuous, fx is continuous at the point 0, but not differentiable because limit extends to 0 plus fx minus f0 by x minus 0, this is equal to 0, this is equal to x square, fx equal to x square here, and for right left hand limit extends to 0 minus this fx equals to x, so this is equal to 1. So fx is not differentiable at x equal to 0 but continuous there, and similarly we can find the same result for x equal to 1. For x equal to 1, fx is continuous but not differentiable at that point. So f is not differentiable at two values of x equal to 0 and x equal to 1. Next question G. If y equal to x to the power 4 plus 2x cube minus 3x square minus 4x, then which one of the following statements is correct? Which one of the following statements is correct? But the question may be wrong. The correct option is 2 and 3. First we see this x to the power 4, question number G. First we draw the graph. y equal to x to the power 4 plus 2x to the power 3 plus minus 3x to the power 2 minus 4x. So this is the minimum point, minus 2 minus 4, and this is the local minimum, and this is the also global minimum. Also this is the local maximum. This point is x equal to minus half. So from x equal to minus 2 to minus half, this function is increasing function, and this point is 1 minus 4, x equal to 1. So this is the local minimum, and minimum value is minus 4. Also global minimum, these 2 points are global minimum. So from x equal to minus half to x equal to 1, this function is decreasing function. Minus half less than x less than 1, and minus 2 less than x less than minus half, y is increasing function for this, and less than minus half, the function is decreasing function, and greater than 1, when x is greater than 1, function is increasing function. It is clear from this graph. So now we find this function y is say fx equal to x to the power 4 2x cube minus 3x square minus 4x. Find f dash x and f dash minus 2, f dash minus half, and f dash 1. So f dash x equals to 0, f dash x equals to 0, we find this is the cubic function. So we find three roots. Here are 3 real roots. This is the minus 2, minus half, and 1. Cubic function, 3 roots. So f dash equal to 0 this. So these are 3 stationary points, local minimum or maximum at these points may be occur. If x is less than minus 2, suppose x equal to minus 3, then f dash minus 3 equal to minus 40 is less than 0. So for less than minus 2, f is decreasing function, and when minus 2 less than x less than half, minus half, and suppose x equal to minus 1. So for minus 1, f dash minus 1 is positive. So if it's increasing for minus 2 less than x less than minus half, and you can easily find this f double dash and test for f double dash at the point minus 2, at the point minus half, and at the point 1, and you can easily find this the f double dash at the point minus 2 is the greater than 0, and this is the maximum and the minimum, local minimum, and for this x equal to minus half is the local maximum. F double dash at this point is negative, and this positive, local minimum. Only there are 3 stationary points here. So other points, either function f is increasing or decreasing, and when x greater than 1 and let x equal to 2 and f dash 2 is greater than 0. So f is increasing for x greater than 1, x greater than 1. Sorry, this is 1. Actually, this is 1, not 2. X greater than 1, this function is increasing function. Next question. H. Which one of the following statements is correct for the function f(x) equal to x cube? Of correct option is 3. F has neither local maximum nor local minimum at x equal to 0. Actually, this is the point of inflection. So, if we this y equal to x cube, and this is the graph. So this is the y equal to x cube. This is the graph. This is the for negative x when x is less than 0, and this function is the concave downwards, and this is the concave from upwards, that is convex from downwards. So convexity changes at this point x equal to 0. Obviously, see that this is the tangent at this. No, so there is no tangent here because the function this. So value of this function is 1, 0. Value of the function is 0. Actually, this is the point of inflection, x equal to 0. So actually, necessary condition at x equal to 0, f has neither local maximum nor local minimum. It is a point of inflection. If we find f dash x equal to 0, f dash x equal to 3x square, f double dash 6x, and f double dash 0 equal to 0. So we cannot conclude for x equal to 0 either maximum or minimum. If triple dash x equal to 6 not equal to 0, obviously. Actually, point of inflection, what is the point of inflection? The point of inflection is a point on a smooth plane curve at which curvature changes sign. It is a point where the function changes from being concave downward to concave upward, or vice versa. This is the concave, and this is the concave downwards, and this is the concave from upward. And necessary condition for the point of inflection and C be a point within open interval AB, and if double dash C exists, if double dash C exists, and if F has a point of inflection at C, then F double dash C equal to 0. But converse may not be true. That is, F double dash C equal to 0 does not imply C is a point of inflection. For example, this fx equal to x to the power 4 and C equal to 0. So f dash this, f double dash is this, f double dash 0 equal to 0, but x equal to 0 is not a point of inflection. Note that if double dash C may not exist, but C could be a point of inflection. So condition is the f double dash C if exists, and if f has a point of inflection, then f double dash C del double dash C equal to 0. So at the point C, there is a point of inflection, but f double dash C does not exist. For example, this f double dash 0 for this function fx equal to x to the power 1 by 3 may not exist here, does not exist here. And the sufficient condition for point of inflection, and C is a point within the open interval AB, if f double dash C equal to 0 and if triple dash C not equal to 0, then C is a point of inflection. Note that it is possible that C is a point of inflection of the function f, and f triple dash C equal to 0. is a point of inflection if triple dash c equal to 0. For example, if x equal to x to the power 5. So the general condition for sufficient condition, general sufficient condition is this: if fn equal to fn any derivative at the point c equal to 0 or n equal to 1, 2, k minus 1, but if k is derivative at the point c not equal to 0 with k greater than equal to 3 and odd, this k is derivative k is odd, either 3 or 5, this is not equal to 0. If 3 equal to if triple dash c equal to 0, then we have to find if fifth derivative at the point c not equal to 0. Then fx has a point of inflection at x equal to c. So this is the sufficient condition for the point of inflection. Next question: which one of the following function is uniformly continuous on the domain as stated? Correct option is 2. Fx equal to 1 by x, x belongs to the this closed interval 1 to infinity. This let's see greater than equal to 1, and fx minus fc equal to this, and c greater than equal to 1 and x greater than equal to 1. So mod of cx greater than equal to 1. So mod of fx minus fc less than equal to mod of x minus c. Let us choose epsilon greater than 0. Then for all x greater than equal to 1, satisfying mod of x minus c less than epsilon, mod of fx minus fc is less than epsilon for any c greater than equal to 1. C is any point greater than 1. C is any point. This shows that f is uniformly continuous on this interval 1 to infinity closed interval. Now, if x equal to x square, x belongs to real number, is uniformly continuous in any closed interval AB for a greater than equal to 0, but not uniformly continuous on this interval closed interval a to infinity greater than equal to 0. But as here in the R, so the real numbers are, so it's not uniformly continuous here. And this if x equals to tan x, x belongs to the open interval minus pi by 2 to pi by 2, is not uniformly continuous, because we know that if it's continuous on an open interval AB, then f is uniformly continuous on AB if and only f of a plus 0, this is the lower bound, this for a plus 0, right hand limit for this lower bound, and a b minus 0, left hand limit for the upper bound. So both limit exist finitely for this open interval. This is the condition for this open interval. But here tan x, when x tends to pi by 2 minus, this tends to plus infinity tan x, and when x tends to minus pi by 2 plus, this tan x tends to minus infinity, so not finite. So obviously f x equals to tan x is not uniformly continuous on this. And also this box function, that is the greatest integer function for x within the closed interval 0, 1, closed interval 0, 1, actually closed interval 0, 1, fx equal to 0 when 0 less than equal to x less than 1, and fx equal to 1 when 1 less than equal to x less than 1. And if it's not continuous, x equal to 1, because at the point 1, this the left hand limit is 0 and the right hand limit is 1, so not continuous at the point 0, 1. And the I is the interval, I be the interval, and function f from I map from I to R. If is uniformly continuous on I, implies if it's continuous on I. So if it's not continuous on I, contrapositively, this implies if it's not uniformly continuous on I. So at the point 1 it's not continuous, so obviously it is not uniformly continuous on I. Next question, last question G. Which of the functions does not satisfy the condition of Rolle's theorem in the closed interval minus 1 to 1? Option 2, 1 by x square. Because if we draw the graph of 1 by x square, this is the 1 by x square, and from limit from 0 plus, this plus infinity, and 0 minus of this function 1 by x square, also plus infinity. So fx has an infinite limit exists at the point x equal to 0, infinite discontinuity. And the first condition of Rolle's theorem, the f is continuous in the closed interval AB, is not satisfied for the function x equal to 1 by x square within the closed interval minus 1 to 1, because 0 is the point of infinite discontinuity of the function 1 by x square. The other functions x square, 1 by x square plus 4 root over x square plus 3 are all satisfies the Rolle's condition, satisfies the condition of Rolle's theorem. Hence the correct option is 2, 1 by x square. This completes the MCQ 2020 of the paper CC-5. Thank you for watching this video.